As we saw in the last lecture, if you connect an inductor and a capacitor together in a circuit, the result will be current that oscillates back and forth. However, we can also drive this current with an oscillating voltage source. This is known as alternating current, called so because the current goes in opposite directions. This is in contrast to direct current, which is what we've done for most of the time we've looked at current in this course. And that's called direct current because it's always in the same direction. Now, with alternating current, the math can get pretty hairy pretty quick. And there are a number of tricks that you will learn if you get into alternating current. For now, I am going to try to keep things as simple as possible, which, as you can probably see by these notes, is not that simple. Now, I'm going to try to explain this. So, this is a new way of notation, a new way of describing what's going on. So, current as a function of time. In alternating current, current and voltage are both sinusoidal. They're both described by a sine or a cosine. And sine and cosine are the same thing, just shifted from each other. So the most generic way we can describe current in an AC system is current is equal to some I naught, this is the amplitude of the current. In other words, it's the maximum value that the current will ever reach, times the cosine of omega t. Omega is again the angular frequency, although this time it is the driven angular frequency. It's not what you get when you do 1 over square root of 1 over LC or anything like this. This omega is determined by the source. This is time. As time goes on, the current wiggles back and forth. And this term right here is called the current phase. That is some value that represents where current is in its oscillation relative to some pure sinusoid. Now, because this is quite a mouthful to write, I'm going to use a kind of abbreviated notation. This is represented by I twiddle phi. So this I naught twiddle, that represents that it is magnitude of I naught, and we have a cosine of omega t in it. And angle phi means that it has a phase angle of phi. This is called a phasor. It's kind of like a vector. It has a kind of direction in this phase, but it's not exactly a vector, and we will get into a bit of phasor mathematics in a bit. Now, if we have this current, I naught cosine omega t plus phi, or I naught twiddle phi, we can use Ohm's law to find the voltage across it. Because after all, V is equal to I times R, and that's not changed by being an alternating current. I is I twiddle, so I twiddle R times phi is equal to V twiddle phi V. So the magnitude of V twiddle is equal to the magnitude of I twiddle R, and the phase angle of voltage is equal to the phase angle of current. With a resistor, voltage and current go together. Now with inductors or capacitors, this gets interesting. So the voltage across an inductor is given by L di dt. Well, we can take the derivative of this. So to take the derivative of cosine, you pull the omega out and change it to negative sine. So L times di dt is negative omega times I naught times sine of omega t plus phi. Now, negative sine is equal to cosine plus 90 degrees. So we could replace this, the negative and the sine, with just a single cosine by adding in 90 degrees in here. Which means that in our phasor notation, we can say that V twiddle phi v, is equal to I twiddle times L omega times phi I, or times phi I plus 90 degrees. The magnitude of v is equal to the magnitude of I times L times omega, and the angle of v is equal to the angle of I plus 90 degrees. One way of saying this is that when you have an inductor inside alternating current, the voltage is always ahead of the current. If you think about this, when you going back to when we first had an LC oscillation, in this case there was a lot of voltage across the inductor but no current. Later on, the current built up, but the voltage dropped down to 0. Being driven by an AC source, the voltage will always be in front of the current and will always try to drive the current to be more like it, but the current will never be able to catch up. Now we could do some similar math with a capacitor, recognizing that the charge on a capacitor is equal to the integral of I dt. I'm just going to shorten it and say that the voltage across the capacitor is equal to I over C omega, and the phase of the voltage is equal to the phase of the current minus 90 degrees. In a capacitor, voltage always trails current. Now notice in all of these cases, we can say that voltage is equal to I times something. For a resistor, it's I times R. For an inductor, it's I times L omega. And for a capacitor, it's I times 1 over C omega. So we could make a generalization that there is a new quantity, which is represented by the letter Z. It's called impedance. And that is the general form of resistance for AC circuits. So V twiddle is equal to I twiddle times Z. To account for the phase, think of Z as a vector. The Z vector has two components. There is the resistive component, which is just equal to the resistor. And there is the reactive component, which is the combination of inductor and capacitor. We can say the magnitude of Z, when using this formula we're looking at the magnitudes. The magnitude of Z is equal, we use the Pythagorean theorem, the square root of r squared plus x squared. We can also say that this impedance has its own phase angle, called theta z. Theta z is the angle of this vector relative to the I direction. And so finding theta from components, theta is the arctan of opposite over adjacent. Now recall when we looked at arctans in Physics 1, there were always these caveats. Fortunately for us, we never have to worry about negative signs in this case because resistance will never be negative. So arctan in your calculator will always give the correct answer as long as there is resistance. If there's no resistance, then phi z is either pi over 2 or negative pi over 2, or in degrees, 90 degrees or negative 90 degrees. But you won't be able to put in over 0 in here. So we still have to watch out for that, but the value you get will be correct. Now, the reason I have decided to call these, well, the reason I'm calling these phasors instead of just straight up vectors is because multiplication and division do something different with these angles. You see, for vectors, when we want to multiply two things together, we either need to use a dot product or a cross product, and there are specific rules for that. But for phasors, if we want to multiply two phasors together, we multiply their magnitudes and then add their phase angle. So we could say that the phase angle of voltage is equal to the phase angle of current plus the phase angle of the impedance. Now you will also often see diagrams looking like this, trying to draw these as vectors. and it should give all the same math as here.